Let's replay our movie here, but this time let's accelerate it by a factor of 10. So it goes like, look at this again. And look at the long time behavior. After everything is mixed, and mixed further. Do you see any color variations in this plot anymore?
The center is wide, other than that.
So if I color the R parameter using the spectrum of light, what does white mean? White means everything, right? All the parameters. Actually, if I look at a very, not just a movie, but like also average it for much longer time, this is the picture I get. So most of the phase space is white. That means everything is mixed up. But there are some small red and blue here. That means the long time distribution is not really as sensitive as what we saw before in the time history. But there is a little slight sensitivity we can see from the distribution. And that should be the sensitivity we compute. Right? We should be computing the sensitivity of the slight shift of the density of the distribution compared to, as opposed to instantaneous quantity. Okay, and you can also see that from the quantity that is averaged over much longer time. This looks like a very smooth curve. So let's look at the mathematical problem again. So for a uniform hyperbolic dynamical system, so uniformly hyperbolic is an assumption of an ideal class of chaotic dynamical systems. And let's look at an ergodic time average. An ergodic time average means a time average that is independent of the initial condition of U. Okay, that can often be the quantity of interest in engineering simulations. So we can prove that. So actually, Ruel proved that, a French mathematician proved that the derivative of the long time average, infinite time average, is differentiable with respect to the parameter in the system. That is what we just saw qualitatively. But the thing is that you cannot compute the derivative by taking derivative of a finite time average. As you take the finite time average, the time average to bigger and bigger, this derivative diverges instead of converging to that true derivative. So that's the mathematical problem I'm set up to solve. And this also is here. This is the reason for here is all these oscillations coming here. Okay. And all these oscillations are because trajectories with similar parameters diverge, right? And what if we can compute a pair of trajectories with similar parameters that doesn't diverge? So this is a method I called shadowing. So shadowing is a concept that if you take a simulation, you change the parameter, instead of starting from the same initial condition, you start from a very carefully chosen different initial condition, such that the simulation with the perturbed parameter actually stay close to the original simulation. This is shadowing. This is a demonstration of what shadowing does. So the green simulation follows a slightly perturbed differential equation, but it stays close to the blue trajectory because I also perturb the initial condition in a very specific manner. And if I do this, what is no longer equal can be equal because now I can change these two limits. Okay, so what are these two limits? One limit is the limit in the definition of the derivative. A derivative is also a limit of when this s prime goes to s. The other limit is the t goes to infinity. The averaging length goes to infinity. The derivative of the infinite time average takes t goes to infinity first, and then take delta s goes to 0. But in the simulation, we can only take the limit the other way. We cannot take the simulation length to infinity, right? So we have to take a derivative first, and then use a pretty long simulation trying to capture the derivative. So you need to exchange these two limits, and the condition of the exchange. So the condition of this exchange is uniform convergence. So the mathematics goes this way. So if the objective function itself is uniformly smooth, that is usually satisfied. The thing that is not satisfied with previous method is that the perturbed solution has to converge to the unperturbed solution uniformly by uniformly in T. That is not satisfied with previous method. With previous method, because as T grows larger and larger, the trajectory diverge, so you need a smaller and smaller delta S for this U to be similar to that U, right? But if you can have uniform convergence, then you can exchange these derivatives. So if you have uniform convergence, the derivative of the infinite time average is actually equal to the infinite time average of the derivative. So this notion of uniform convergence is the work of Weierstrass. It's called Weierstrass. So this is him. And if you can exchange these derivatives, then you can approximate the derivative we want using a derivative of a long time average. So this is the interesting part on the new math. Now, how do you guarantee the uniform convergence? So to prove uniform convergence, we've used one of my favorite theorems here, the implicit function theorem. Okay, the implicit function theorem is usually used in finite dimension, but here we're using infinite dimension. So if the residual here is the residual of the whole differential equation that is parameterized by S, then that residual equal to 0 actually defines a smooth implicit function that goes from S to U. Okay, right? S is a parameter. As you change S, the U that satisfies this constraint is a smooth function of S. So this is done not in a vector, well, not in a finite dimensional vector space, but in a Banach space. In a Banach space with metric of the supremum of the absolute value of U. Smoothness in that space guarantees uniform smoothness, right? Because the norm is defined as the supremum over all time. So if I can prove smoothness in this space, I get uniform smoothness. So that's what makes the math work out. And the only thing left is we need to prove the Fauché derivative of R to U has bounded inverse, and that is much easier than doing things in the nonlinear world because the derivative is linear properties of the dynamical system. And here is what we use the uniform hyperbolicity of the system to help here. Okay, so we had a paper that basically proves that the derivative holds true if you solve this minimization problem. And this minimization problem is what guarantees that the solution approximates very well to the non-computable implicit function we know exist, but like we can also approximate by solving the least squares problem. So least square shadowing, the method basically works like this. So you have a dynamical system, you solve it, you approximate the long time average using a finite time average, and you are going to approximate the derivative of the finite time average using a derivative of the finite time average. The trick here is that this du/ds cannot be the solution of the linearized initial value problem, right? If du/ds is the solution of the initial value problem, that's exactly the complex derivative example we just demonstrated. It has to be the linearized shadowing problem. Okay. Okay, so what is the linearized shadowing problem? The linearized shadowing problem is this. So instead of linearizing the initial value problem, we linearize the L2 regularized problem without initial condition. So that is, we minimize the L2 norm of the linearized solution such that V satisfies the linearized differential equation. And to solve that shadowing problem, we tried many methods. So this shadowing problem is very, very interesting. So first of all,
what is f sub s, the last term in the second equation?
This is the derivative of f with respect to s. This is the derivative of f with respect to the state u. So this is a square Jacobian. This is a matrix with whatever shape s has. Right. So this is a constraint that is almost full rank, but not, because we don't have any initial condition on this. Okay, so the most straightforward method is, okay, why don't I search the initial value space of V? And then for each initial value, I solve this equation, I compute the norm, and I search for the initial value that gives the least norm. Is that a good idea? It's a good idea unless you have a chaotic system. If you have a chaotic system, if you change the initial condition a little bit, the V changes by whatever crazy amount, and you get an extremely ill-conditioned optimization problem to solve. It's as bad as the original problem you are trying to get. So the first method that worked is by actually looking at the system as a linearly constrained quadratic minimization problem. Right? This is a linear equation. Thanks to the fact that we linearize this equation, this is a linear constraint. The objective function is quadratic. Okay, what does that mean? Quadratic objective function, linear constraint. Is that easy problem, hard problem? Easy, right? Because the derivative of a quadratic objective function is linear. So I have a linear constraint, linear derivative. I get a set of linear equations to solve. So I can solve this problem by solving basically a linear equation. Okay, so that is the first method that worked, and that is the method that I showed in the NASA Form 3D example.